We say a neural network learns. But what does that actually mean? There's no understanding in there, no studying. Learning for a network is something far more mechanical. And once you see it, the magic turns into a beautifully simple loop you could almost do by hand. So let's watch a network teach itself. Training a neural network is really just 4 steps, repeated millions of times. 1. Make a guess. 2. Measure how wrong it was. 3. Figure out which way to nudge each knob to be a little less wrong. 4. Nudge them a tiny bit. Guess, measure, nudge. Again and again until the guesses get good. That's the whole thing. First, what's actually being tuned? Start with a single neuron. It does something almost laughably simple. It takes its inputs, multiplies each one by a weight, adds them all up, and passes the result through a little function that bends it into shape. Inputs in, one number out. And those weights? Those are the dials we get to turn. Now wire millions of these neurons together in layers, the output of one becoming the input of the next, and you have a neural network. It's really just one enormous function with millions of those weights inside it. And learning is nothing more and nothing less than finding the right numbers for all of them. Here's the scale of the problem though. A modern network has billions of weights, all tangled together and nudging one ripples through everything downstream. Nobody could possibly set these by hand. So the entire game is this. How does the network find good values for billions of dials, completely on its own? The next steps are the answer. Step 1. The forward pass. It all starts with a guess. You feed an input in at the bottom. Say the pixels of a handwritten digit. It flows up through the layers, each neuron computing its little weighted sum, layer by layer, until the top spits out a prediction. I think this is a 7. That journey from input to output is the forward pass. And at the very start of training, the weights are completely random. So this first guess is basically nonsense. It might call a 7 or 2 with no real confidence at all. And that is totally fine. In fact, a wrong guess is exactly what we want, because a wrong guess is something we can measure. Step 2. Measure the wrongness. To improve, the network needs a score for how badly it just did. That's the loss. A single number capturing the gap between the guess and the right answer. Guess close to correct? Low loss. Wildly off? High loss. And the entire goal of training collapses down to one sentence. Make the loss as small as you possibly can. And here's the key link. The loss depends on the weights. Different weights give a different guess, which gives a different loss. So you can picture the loss as a vast landscape, a surface, where every possible setting of the weights is a location. And the height at that spot is how wrong the network is there. Training is a search for the lowest valley in that landscape. Step 3. Roll downhill. But this landscape has billions of dimensions. You can't see it, you can't map it. You're just standing somewhere on it, blindfolded, trying to get to the bottom. So what can you actually do? You can feel the slope, right under your feet. And if you always step in the steepest downhill direction, you'll eventually reach a valley. That is gradient descent. The gradient is just the mathematical word for that slope. The direction in which the loss increases fastest. So you simply step the opposite way, downhill. Compute the slope, take a step down, recompute, step again. Each step lowers the loss a little. Roll downhill over and over until you settle at the bottom. And how big a step do you take? That's the learning rate. Maybe the single most important dial in all of training. Too small and learning crawls, taking forever to get anywhere. Too large, and you leap clean over the valley, bouncing around or even flying out and exploding. Get it just right, and you glide smoothly down to the bottom. So the plan is clear. Feel the slope, step downhill, repeat. There's just one enormous problem hiding inside it. To take a step, you need the slope for every single weight, billions of them, and you need it fast on every step. computing that the naive way would be impossibly slow. The trick that makes it work is the real hero of deep learning. Step 4. Backpropagation. That trick is backpropagation. The insight is about blame. The error at the output was caused by the weights, but the ones near the top are more directly responsible, and the ones deep down contributed only through everything that came after them. So you assign blame backwards. Start at the error and flow it back through the network, layer by layer, handing each weight its fair share. The engine that makes this exact is the chain rule from calculus. It says, if A affects B and B affects C, then A's effect on C is simply their two effects multiplied together. A neural network is one long chain exactly like that. So to find how a deep weight affects the final loss, you multiply the little effects back along the chain. Backprop is just the chain rule, run in reverse, across the whole network. And here's the genuinely beautiful part. It is shockingly efficient. In one forward pass, you make the guess. In one backward pass, you get the slope for every weight at once, billions of them, by cleverly reusing the calculations as you go. One forward, one backward, and you know exactly how to nudge every dial. That efficiency is the thing that makes training deep networks possible at all. So now the full loop finally clicks together. Forward pass, guess, loss, measure, backprop, get the slope for every weight. Gradient descent, nudge every weight one step downhill. Then do it again, on the next example, and the next, millions upon millions of times. And slowly, the loss falls, the guesses sharpen, and the network learns. Making it faster, optimizes. Plain gradient descent works, but it can be slow and jittery, getting stuck on flat spots, rattling back and forth across narrow valleys. So in practice, we use smarter steppers called optimizers. The first big idea is momentum. Like a ball rolling downhill, it builds up speed in a consistent direction, powering through flat patches and smoothing out the jitter. And the one almost everyone actually uses is Adam. It's clever. It gives every single weight its own personal learning rate and adapts it on the fly. Bigger steps where the slope has been gentle and steady, smaller careful steps where it's been steep and noisy. Momentum plus per weight adaptation. It's the default that just works, and it's quietly training most of the models you've heard of. What goes wrong? A few things reliably break training. The learning rate, again. It's the dial people get wrong most often. Set it too high, and the loss explodes off to infinity. Set it too low, and it flatlines, learning almost nothing. There's a narrow sweet spot, and honestly, finding it is half the battle of training a network. Then, in very deep networks, there's the vanishing gradient. As you multiply those little effects back through dozens of layers, they can shrink towards zero. So the earliest layers receive almost no signal and barely learn at all. This nearly killed deep learning until fixes like better activation functions and the residual connections from our transformer video came to the rescue. And what about getting stuck in the wrong valley? A local minimum. It sounds terrifying, but here's the twist. In billions of dimensions, true traps turn out to be rare. There's almost always some direction that still leads downhill. In practice, gradient descent reliably finds a valley that's plenty good enough. Simple, blind, downhill steps, scaled up massively, really are enough. So that's how a network learns. No understanding, no studying, just guess, measure, blame, and nudge. Repeated until it's right. Backprop finds the slope, gradient descent takes the step, and an optimizer makes it graceful. Billions of dials, all rolling downhill together toward a setting that finally works, mechanical, relentless, and, scaled up far enough, genuinely intelligent. So the next time you hear that a neural network learned something, you'll know the real truth. It rolled downhill. One simple step, taken a billion times, until the guessing got good. Subscribe for more such intuitive videos.